Alright, in our last class assignment for the structural equation modeling class, we covered item response theory. Now, item response theory in R is slightly controversial. Some people say that the packages are no good. And I would tell you to do some of your own research before deciding which package or which program to use. I've also used ParScale and Bilog, which are owned by SSI. I would love to be able to do it in R, and so I'm hoping that these packages I'm going to show you are pretty good. They look like they are, but don't take my word for it because I'm most definitely not an expert in item response theory. I do know how to do it though, and I will give you the very brief version of it because this can be extraordinarily complex, but we're going to do some very simple models just so you can get your feet wet. And so one of the first things that you'll want to do is always load the libraries, right? But there's a specific package called LTM, okay? And I have LTM on my computer already. But one of the problems with LTM is if you have a Mac, it's grumpy, which is a nice way to say it doesn't really work sometimes, because sometimes MSM, as you see that loaded down here, oops, that's polycore, and MVT norm will not install. The default is to include dependencies in R, but it doesn't always work. And so for some reason, I have a fairly new Mac, and I'm running Mavericks. Let's see what I have exactly. There you go. Oh, just kidding. I'm running Yosemite, so that might be the issue. I upgraded from Mavericks. And so there was something particular about my system that did not have Fortran, which seems a little weird because Fortran's old school. And so in my notes, I found here's how to fix it. Let me open that for you guys. I Googled a lot and then finally figured out, it's towards the end here, if you have a Mac and you get this, an error message about non-zero dependencies, there's some very specific code that you can run in terminal. So what you do, go to find, search terminal, let it open terminal, and then cut these lines and paste them one at a time. That will install this G-Fortran package for you, and then you can install LTM or MSM or MVT norm, whichever one is the problem, in R. If it installs perfectly the first time, move on with your life. If you get this non-zero dependencies, I think that's what it was, error, here's the solution that worked for me. So there's my warning for Mac peoples. All right. So that being said, we're going to we've loaded the LTM library. And what I'm going to do is test a couple different models. Let me go back to Word here, on some data. So I have an ed psychologist who was down the hall from me, and he gave me some data from a test he had just given. So let's load those. So let's load up the data. So I'm going to import data set from text file. I'm going to go through and figure out where I have it hidden, folders and folders on my computer. Assignments, here we go. Let's call this data, and it does have the header. So, oh no, it does not have a header. So V1, V2, V3, because I didn't put in question 1, question 2 in his data set. So there are 70 questions with 30 participants. That is not really actually nearly enough to run IRT on, but we're going to try it. And so a wise IRT person once told me, per sample size, whatever runs. Generally, you want lots of people, because the more people you have, the better estimation you're going to get. That's true in any statistical analysis. I've seen numbers 500 to 1,000. Sometimes that's not possible, and so I have just a test me data set on 30 observations, and essentially I could be more precise and better with more data. But this is just a demo, so here we go. But in general, I would probably tell you that 30 is not enough to do a good IRT model. Right? So I am going to try running this as a 2PL and a 3PL. Come back to what that means here in a second. But the first thing I suggested doing is calculating those summary statistics. So let's just pick out columns 2 through 5 and then look at some of these summaries. So the first thing I want to do is drop everything else. So I'm going to get all rows and then give me columns just 2 through 5. And that seriously reduces my data set down. So I have 4 questions and we're going to examine those 4 questions. Now, I want to try and look at a summary. So I'm just going to use the summary function of the data set. And let's look at what we have here. And so if I look at the mean across these questions, I can already tell, and this professor would say this too, that the questions are too easy. So 70% of people are getting it right. Okay. So just a warning, we're going to do dichotomous data. If you want to learn about polytomous data or doing like a graded response model or a partial credit model, what you'll want to do is come back later when we have those videos recorded or find another awesome video. Because this is like purely dichotomous data where there's answers that are right or wrong. And we're really talking about more traditional item response theory where we're looking at ability on a test. But so if you're wanting more of a 1 through 5 kind of scale, that's a different video. So back to that. So I have 0s and 1s, and in looking at this data, I have fairly easy questions. So 70% of people are getting it right. On the third question, nearly everyone is getting it right. Maybe 1 or 2 people missed it. 70%, 86%. So these questions are really easy. So questions that are really easy are going to have the opposite ability measures. That means that since most people are getting them right, they're going to discriminate at the bottom of the distribution. Okay. If that makes 0 sense to you, wait a couple minutes and see if it makes more sense. Okay. But in general, I would say that these questions are very easy. So let's try running a 2PL and a 3PL. What PL was she talking about? Okay. There are actually 3 or 4 different types of IRT models. A 1PL, or a 1-parameter logistic model, PL is more fun to say, is often considered a Roche model, and that is where we're only going to estimate one piece of information. A 2PL adds another parameter, a 3PL adds another parameter, and there's actually a 4PL. I wouldn't recommend it. Okay. So what are the generally three parameters that people estimate? Okay. And that is going to be A, B, and C. But we're going to start by estimating discriminability and generally what's called the location parameter or ability parameter. So the first one we're going to look at is B. And so B is the measure of where things are 50-50. And so when you create a discrimination curve, what we're going to look for is where that logistic curve has 50% of the data below and 50% of the data above. So this is the point right here where the item is the most discriminable. So that is generally the location. So what happens is the difficulty parameter, I knew it was another D, it just wasn't coming to mind. That is sort of a measure of where the item is doing the best job of differentiating people. And so if your parameter is 0, what that means is that this is a z-score on the bottom for ability. The item is measuring the mean of the distribution the best. So think about z-scores, the average is a mean. We got negative scores are below the mean, positive scores above the mean. So if your difficulty parameter or your location parameter is negative, that implies that the question is too easy. Lots of people are getting it right. So it's measuring the lower end of the distribution. So questions that are too easy, everyone gets them. So only the people at the very bottom of the distribution are missing them. Okay. Questions that are too hard, I'm using too easy and too hard kind of colloquially, questions that are harder will have a positive difficulty parameter, because that is where only the top people are getting it right. So everybody else below that is getting it wrong. And that's why I say this is really for just dichotomous yes-no kind of data. Adding the 3PL as a guessing parameter. So sometimes, especially on multiple choice tests, there are questions that are just easy to guess. I mean, if it were written in a foreign language and you had no idea what those squiggles were, you would have a 1 in 4 chance. Now, sometimes guessing parameters will get higher than that because sometimes the alternatives are obviously wrong. And then sometimes guessing parameters flatten out at 0. And you're like, well, if I have a 1 to 4, how is it not 25%? Well, sometimes one of the wrong answers is very tempting. And so the guessing parameter can get actually much lower. So we're going to try both a 2PL and a 3PL and see which one runs better for us. Always simpler models would be better. Okay. And then I skipped slope completely, so let me talk about slope. The A parameter is slope, or discriminability, and that tells you how good the item is at discriminating. So B tells you where it discriminates, A tells you how good it is at discriminating. I've heard a cutoff score of 1 as sort of a good discriminator. That's not a hard and fast rule. And essentially it tells you the steepness of the logistic slope. So you want steeper slopes. That means they're more discriminating, which is good. So like at that point, you know this person's getting it wrong, this person's getting it right. C is the guessing parameter. It's not always used. Now in a 1PL, there's just the difficulty parameter. It tells you where people are getting it right or wrong, but it forces all of the slopes to be the same. That's very tempting, but if you've been in scale development for more than 5 seconds, you will know that some questions are just harder than others, and so some questions are better than others. And so a Roche model is not, it's very easy, but it's maybe not the best idea. This is personal experience, because if I force all the slopes to be the same, if I have some really good questions and some really bad questions, it'll average them all out, and I won't be able to tell you which questions are good and which questions are bad, just where they're measuring. So I like the 2PL and the 3PL, personal choice, or you can test them against each other and see which one runs best. So let's try 2PL now. I'm giving you the very, very brief overview of the differences between those models. So what we're going to do is just say that the model equals. Now this code is very different from the Lavon code that I've been doing because it is a different library. The other thing about this chapter in the Buchanan book is that he talks a lot about item factor analysis and item response theory. Now my brief comment on that is that item factor analysis and item response theory will be transformable. You can get from one to the other in a 2PL sense. If you want to include a guessing parameter, you're going straight item response theory. To me, the biggest difference between these two things really is theory focus. If I am doing scale development and factor analysis and I'm trying to see, do my questions load? Are they matching the latent variables I expected? Is it the right amount of latent variables I've expected? That's more of a factor analysis, and I would go towards maybe an item factor analysis with tetrachoric correlations for dichotomous data. If my goal is instead, where is this question measuring my latent variable better? How good is this question at measuring that latent variable? It's kind of the same as factor analysis. And how guessable is this question? Go item response theory. And so mathematically they may be transferable, but theoretically I think there's kind of a big distinction between the two. So I would say if you're interested in the idea of where's the question measuring better on the latent variable, how good is it, and then how guessable is it, go item response theory. Okay. So that's my brief divergence into item factor analysis. All right, so we're going to use the LTM function because it's latent trait model, I think is what it stands for. Now what you do is you take the data set and you just type in the data set name, which I've called data, and I've dropped it to only the questions I want, so don't include any other random things, data screening, all that jazz. Okay. Is approximately equal to, and you do Z1. Okay, it's always Z1. That's part of the code for this analysis. You can have Z1 and Z2 if it's a multi-trait model. Generally, item response theory is on a unidimensional model. If you're going to go multi-trait models, you should do some more research on which package would be best for you. Okay. The other thing I'm going to do is do IRT dot param is true. Okay. If you leave that off, it will default to giving you something that I'm not sure what it is, and so it's going to be called the slope and the intercept. If you are thinking about this in a traditional IRT way, leave on the true there. Okay. So this is going to be my 2PL. Okay, so that's what this particular code does automatically. So let's run that. It may be quick, it may be slow, it may crash. Now I can do the summary function, but instead I'm going to use the coef function for coefficients. And I'm going to look at the difficulty and discrimination for my four questions. So the difficulty is the B parameter, or the location. Where is this item most discriminable? And so obviously they're all going to be negative because more than half the people are getting it right. And so that makes the question very easy. And so, for example, question 3 has got a negative 3.1. That means only people in this z-score transformation of your ability factor, which in this case is education psych knowledge. Okay. That means only people 3 standard deviations below the mean are missing that question. Okay. And so this difficulty parameter is a z-score of whatever you think the latent variable is. So if the latent variable is ability or IQ or depression, whatever, that means that it's a z, so it's easy to interpret. Only people 3 standard deviations below the mean are getting this question wrong. Everybody else above that is getting it right, so it is really easy. And that shouldn't be too surprising given that the mean of the question is 0.93, so 93% of people are getting this right. Okay. And then the other ones are also clearly way too easy, so having the summary here kind of translates also to the difficulty parameters here. Okay. However, having that summary doesn't tell me how discriminable it is. So questions might be way too easy, but very discriminable. Questions might be way too hard, but very discriminable. So that's the cool thing, is you kind of get more than one piece of information. So discrimination, again, is the slopes. This is B and then A. And they're mostly discriminable items. You might get rid of question 3 if you want to go with that 1 cutoff score. It's pretty close, though. So I would say these are all pretty good questions. They're just maybe too easy. So they're very discriminable on the bottom end of the distribution. If I really wanted to suss out the difference between those A and B folks, I need some harder questions. Okay. So that's what coef will give you. It's the coefficients. I can plot those item response curves. So do plot and then model. And then you kind of have to tell it what to plot. If you don't type anything, it gives you the ICCs. But I'm going to say, give it the type, and let's go ICC. Okay. What is ICC? ICC is item characteristic curve, which it very conveniently labels up here for you at the top. And so these will give you the log curves of the data. All right. Now, it does not necessarily plot all the way out to the end. So this question does not have a y-intercept at 0.3. So when we add guessing parameters, guessing parameter is where it asymptotes. So asymptote means level off. Okay? And so all of these level off close to 0. And this one probably does too. At the moment, it's forced to level off at 0 because we are only doing the 2PL, so it makes all the C parameters 0. All the guessing parameters. So that does not, it keeps going. I just don't have it plotted, okay? So here's my z-score of ability at the bottom. So in this particular example, again, it's ed psych knowledge. The B value is where it's 50%. So if I could draw a line across here at probability at 50%, I could probably add it, actually. If I can remember how AB line works. 0.5, 0. See if that works. Yeah, I remembered something. essentially what happens is at this 50% line, B is estimated by where it crosses that 50% line. So that's how it's getting negative 3.1. And then over here for question 5, 1.32. So it finds the point at which probability is 50-50. Okay. So the this is x-axis here is our ability. This is our latent variable, this thing we're trying to measure. And then this one over here is the probability of getting the item correct. So the probability of getting this question right. Okay. So of course it only goes from 0 to 1 because probability only runs from 0 to 1. And so we're looking for the 50-50 point. That is the B parameter. And that is in all three models, 1, 2, and 3PL. Okay. Now the A parameter lets them have different slopes. So we can tell that 3 is less discriminable than the other ones because the slope is more gentle. And so the steeper the slope, the more discriminable the item is. So let's take, for example, question 5 here, which has the highest discriminability value, highest A. So it's measuring at 1.3, so it's measuring 1 standard deviation below the mean in a very strong way. Okay? And so the steeper the slope, the more discriminable it is. So if you're at 1.33, you're getting it wrong. If you're at 1.32, you're getting it right. So it kind of creates this point, and it says, I'm good at discriminating at this particular point. Okay, so those would be item characteristic curves. If you wanted one curve at a time, what you could do is do item equals 1. Okay, and that would just give you the 1, item equals 2, and that would give you only one of them. So you could do one at a time. Okay. Oh, I'm sorry, it's items, plural. Okay. All right. So that is how to get the item characteristic curve. Let's also plot something else, another useful piece of information. So what we're going to do is do type equals ICC, because that's not confusing, item information curve. And we're going to do items equals 0. Okay. And that was a very specific function to plot the test information function. Okay. And so essentially you're testing the item information curve or characteristics, and that is how much information is each question giving you. So it's sort of a transform of the item information curve. So let's do real quick. Let's do the IICs all by themselves. So leave off the items component. And that gives me the item information curves for each one. So what they're going to do is it's taking that logarithmic curve and translating it into a normal distribution curve, and then gives you a plot of how much information you're getting. So what is information? Well, information is sort of a measure of like how discriminable and where it's discriminable. So it's kind of a combination of all the parameters at once. And you'll see that variable 3 is kind of a sucky question. So it's most discriminable at 3.1 or whatever it was. And the other ones have more discrimination. So the higher the A value, the more peaked these slopes will be. And then the slopes will always be centered over B, because that's where they're the most discriminable. Okay. I read somewhere that the information values over 10 are really good, but that was for the test information function, which is the next picture I'm going to show you. But this will show you like where each question is sort of doing the best. So I'm getting a lot of information right across here because I got lots of distribution curves over there. I'm getting like nothing over here. So if you are doing really, really well on this test, I'm not entirely sure why. So let me plot this one again, the one where it says items equals 0. And that gives me the test information function. The test information function is it's not an average, it's the sum total of all these distributions together. So let me see if I can back up one here. Just gonna put them next to each other. Okay, so it is basically the addition of all of these into one picture. Okay, so zoom. Oops, sorry. Go to the next plot and zoom on that one. Okay, so I am getting a good amount of more data over here than I am over here because of that variable 3 question. So you might leave some questions in that are too easy just to make sure you're measuring the bottom well enough. And if I wanted to be better about this test, I need some harder questions. So I could have some questions that are too easy. I need some questions that are too hard to make this function cover 0 to 2. So I'm not measuring above the mean very well. And so it's essentially a sum total of all of that. Now I have, like I said, I've read that information is best at 10. That's not a hard and fast rule either. But I already know that these questions are kind of too easy, and you will always get more information with more questions. So I really need more people and more questions. And I do have more questions, they just don't run very well because they're all way too easy. So these 4 ran pretty well to give you a good example. Now the other pieces that I am going to show you are fairly specific to R. They're done in different ways in like parscale and bilog. But what I'm going to show you is factor scores, person scores, and item fit. So let's start with factor scores. Now this is much easier when you have a very simple model. When you get more complex models, this becomes overly tedious. But what factor scores does is it shows you the observable response patterns. So I could get all of them wrong, so 0s on all of them, or all of them right. So 16 people got all of them right. And so I have the actual observed value for each one. I have the expected value for each one. You want those to be fairly close, because if you're expecting a lot more people in the area of a distribution than you have, you're missing something. The other thing it gives me is the measure of ability for each one of those. So if I get them all right, it says that my ability is just slightly over average, because this question is really, or these questions are way too easy. So if you're getting them all right, my best guess for you is that you're slightly over average. So I don't know if I can tell if you're a B student or an A student. I can just tell that you're better than a C student. Okay. If you're missing all of them, you're 1.8 standard deviations below average. So this actually gives you the ability for each pattern of response of the responses, which you could then go back and apply to your data set. So if you were wanting to use a weighted scoring scheme, you could find people with each of these patterns and give them different scores. And that to me is the beauty of IRT, because look at here 4 and 5, patterns 4 and 5. We're actually getting the same number of questions right. So we're each getting 3 questions right. Actually 4, 5, and 6 here. Right? So we're getting 3 questions right each. Oh, and through 7. Gosh, I can't count. Right. But if you look at our ability parameters, they're all different. And so it depends on which one I miss, which one, where it's going to tell me I am in the distribution. So if I'm missing the last question, I actually have a lower score than if I'm missing the second question. So that, to me, is why IRT is so neat, is because it allows me to discriminate between people who have the same total score. So we're each getting 3 questions right, but I can now discriminate between those people who's actually got a higher score. Well, if I'm missing question 2 on this exam, that's the really easy question. So I have a slightly higher score than some of these other people, okay, who are missing some of these other questions. All right, so that's factor scores. Person.fit gives you a p-value of if that latent score is appropriate. Okay, and so this is a little weird. With SEM, we always want things to be non-significant, because that means that we've modeled it appropriately, and so it's no different than the way the model is in the real world. And so here's the idea. The alternative you're testing is that it's an inconsistent response pattern. And so that would be bad. You want the response pattern to be consistent with what you're modeling. And so you actually want the p-values here, the probability of an inconsistent response pattern, to be non-significant. So you want those to be not less than 0.05. Okay, and there's only one really that is less than 0.05. So this pattern for 5 may or may not be any good, is essentially what it's saying. And then number 7 is also kind of close. Now, you have to keep in mind, if I scroll back up, the pattern for 5 is measured by 1 person, and for 7 is by 1 person. So that's not really enough people to have the best estimator for. So you got to take it with a grain of salt with only 30 people. And then the last thing we're going to do is item.fit. So item.fit. And this tells you if the items are consistent with the model. So a significant value would imply that the items are bad, essentially. They don't fit with the model. And again, grain of salt, because chi-square is a biased parameter, and so generally if you have lots and lots of people, your chi-squares will be significant, but taken into account with other things like A and B, it does look like question 3 might be just a lot of trouble. It's really, really easy. It's only measuring the bottom 1% of data. I think it had the lowest discriminability parameter, so we might consider getting rid of item 3. All right, what we're going to do now, so all of that's the 2PL. Now let's try the 3PL. And so on the assignment, I asked people to include the following. We looked at those pictures. Let's include the guessing parameter now and see if that makes a difference. It would be really lovely if we could just add one little piece of code and it made the 3PL, but not quite. So let's say model 2 is, now the 3PL is the 3-parameter model, so TPM. You type in the name of the data, so it's just don't call data. And then you tell it the type. So we're just going to ask for a latent trait model. That's the normal one. And I still want to do item response parameters are true. And so it's a different function. The LTM function I don't believe will let you do a 3PL. Okay. So let's run that. Cool, it ran. Now let's do approximately the same things. So let's do coefficients. And let's look at the guessing parameters. So now we have the guessing parameters. Okay, this is in scientific notation. If you are like me and you're like, ugh, math, you can turn scientific notation off by doing that. So it's under options, sci-pen equals 999. You would have to do that every single time you open R, but that's how you turn it off. And now I can run those coefficients again and look at them in non-scientific notation. If you're used to scientific digits, go ahead and be awesome. I hate thinking about e to the -6 because it gives me a headache. Okay. And so look at these guessing parameters. They're essentially 0. So these items are really, really easy. And so when items are really, really easy, they often can have guessing parameters that are kind of high. You would think like it's easy to guess, but you have to think about guessing parameters are really to measure how guessable it is if you had no idea what the hell the answer was. And so just because an item's easy does not mean it's easy to guess. If an item's easy, it's easy to know because you know it. It's not easy to guess. Those are kind of separate and separated out into two different ideas. So guessing, remember, is if I have no clue what it is, how easy is it to get the right answer? Whereas difficulty is if I was supposed to know what it was, how easy is it to get the answer? Okay. So the guessing parameter is very, very close to 0. So I imagine that this model as a 3PL is very similar to a 2PL model. And as we create some pictures here, so let's plot the ICCs, so the item characteristic curves. You will notice that it is essentially the same picture. It's like so close, it's hard to tell. And so it essentially is the same picture because that guessing parameter is 0. So it doesn't really change a whole lot by adding it. So there's your characteristic curves. We talked about what the difficulty and discriminability meant, but if you wanted to look at them and compare, I could go back up here. They're essentially the exact same. Because adding that guessing parameter didn't really help us any. Let's plot the TIFF. The test information function should also look the same because I'm not adding any more information by adding that guessing parameter. If your guessing parameter was very necessary, i.e. they were not 0, you would get better fits. So we can do the same thing we did before, factor scores, and look at each pattern of data. So these z values will be slightly different, but it's essentially the same idea. We could do item fit. Oh, sorry, I've skipped person.fit. So I can look and make sure that most of my people are being measured appropriately, and it's going to be the exact same numbers. And then item fit, yeah, question 3, or variable 3, or question 2 is still really bad. Now, if I want to compare the two between each other, other than just kind of looking to see if it fits better, how could I do such a thing? Well, you could do the ANOVA function, but it gets very grumpy if you try this. So if you're used to basic statistics, the ANOVA function in R does not do an ANOVA. And that is something you have to get over kind of quickly. The AOV function does ANOVAs. There are about 10 different packages to make ANOVAs easier, but the ANOVA function is not for basic ANOVAs. It's to compare two models to each other. And so we could do that. So I could do ANOVA, model 1, model, I think I just called it model actually, right? Yeah, and model 2. Okay. It's like, hey, don't do that. That's not nice. What that did for me was it showed me the AICs right on top of each other. And so the ANOVA function is actually going to compare the log likelihood values, and since the log likelihood values are exactly the same, it's kind of like grump, grump, grump. But I could use the AIC to tell which model is better. Now, lower AICs are better. There's not really a good difference score for the two. The other thing I can do is use the summary function to pull those AICs, and those pop up at the top. So here's the exact same information, just in a slightly different format. And I can do summary of model 2. The only thing I don't like about this is the way it lays out guessing parameters. It does tell you the values and, wait, did I get the right one? Yeah. The guessing parameters are just much smaller than this. That's why it looks like 0. I like the coef function because it lays them out by question. It's a little easier to read. But then here's the log likelihood and the AIC. So it's the ANOVA function is grumpy about us doing this because they're so similar. Now sometimes if you drop questions, like if you go, ooh, question 3 is bad, and I drop it, and you try to run ANOVA, it won't run because you're using different data. But you could just use the summary functions to compare those AICs. Okay, so simpler is better. So the 2PL model is better because adding that guessing parameter didn't help. And so because it didn't help, we want to go with the simpler model and just force them all to be 0. Okay, so the 2PL is a better estimate of this data. It's not guessing. So which model is better? The 2PL. Is the guessing parameter necessary? No. Okay. And then we kind of talked about these already. So we talked about which items are good for discrimination. We want the A values to be high, so the discriminability values. Which questions measure below average ability, that's the difficulty or B parameter, sometimes called the location or threshold. And so they're pretty much all measuring below average ability. We don't have above average ability questions. For factor scores, the factor.scores showed us that we have about the right number of people we would have expected in each component or each pattern of data. Those patterns appear to fit the model. A couple of them don't, but we're only being measured by one person. And the items are so-so. The chi-square values are significant, but they seem to be good items, and I would probably try to measure more people to get a better estimate of what those items should be. Right? And so that is your very brief overview of IRT. There are so many other types and functions and ways to measure if items are functioning different for different people, so much like a multi-group analysis in CFA. And so this is just your very simple, can I see where the item's measuring the best, and then how good is that item measuring, and then is the item guessable?